welcome back. A few weeks ago I promised you more content on the CNC router, and here we go. I have some minor topics and also a project to show you. I had to make a bunch of frames out of aluminum for 7-inch touch displays that go into medical peristaltic pumps. So the coolant I'm running in the Fogbuster MQL is pure isopropane alcohol. I'm doing this because I had very good experience with the same coolant on Datron machines. Datron machines, you can look them up on eBay. They're on YouTube. They're famous for being very fast router-style machines, and forever they used isopropane alcohol as a coolant because it prevents chip welding. It gives a little bit of lubrication because any liquid does, even water is lubricating, and it flashes off very quickly. Means you end up with a clean and sterile part and clean dry chips. These are some of the chips from recently, and as you can see they're bone dry. This is 5083 aluminium, which I had to mill with cooling because it's quite soft. And as you can see, the chips are dry and clean. So perfect for recycling. And also it makes cleaning the machine and the part very easy, because you can just dust it off with a dry brush or blow them away with compressed air. This stuff, during 2020, it was a bit hard to get pure isopropane alcohol for obvious reasons, but now the supply has evened out and you can buy it readily available. I get this stuff on eBay in 5-liter buckets, and I'm just here topping off the container. Yeah, I'm not filling it completely. I'm leaving some gap for air above the liquid. And I have the Fogbuster itself mounted to the gantry of the machine because I wanted the container to be about the height of the nozzle. That's also the recommendation by the manufacturer. That helps consistency in feeding the liquid. The container, when in use, is pressurized, and the air pressure on top of the liquid will push the liquid through this hose, through the drag chain, through the C-axis to the Fogbuster itself. So it's not a self-feeding system like a Noga Mini Cool, which are reasonably reliable at best. This, as a forced system, works more reliable. It still has issues because pressure regulators at low pressure are a little bit sketchy. You would have to cascade multiple pressure regulators behind each other to get a very good result. I have a single pressure regulator, and I keep this container at about 1 bar of pressure. You have to do the conversion into non-standard units yourself. So there is one hose coming out here that's directly passed through, that's air, and the other one here is liquid that's pushed up from the container through the nozzle. Let's see how this how the Fogbuster sprays. So let's turn it on. I have it integrated in the CNC controller. A M07 command turns it on. So we're already spraying, but this is a little bit too much, so we're going to turn it back. This valve up here regulates the liquid throughput. Okay, you saw that there is always a little bit of a wet spot from the alcohol hitting my finger, and that's the setting I like. That's very little throughput through the Fogbuster, but still enough not to starve the tool at the cutting edge. You can increase the throughput a little bit when you do drilling or heavy milling, but usually that's enough. Because I'm using a router not just for machining plate, like doing cutouts in plate stock, I'm using them like a regular milling machine, doing all sorts of operations most of the time in vices. I need a way to locate my XY0 for machining. On a VMC, you would have a Renishaw 3D probe or any other means of probing, or on a manual mill, you're using an Edgefinder or a DTI, and the same principles apply to a CNC router, of course. In this case, my spindle can go slow enough to run a Edgefinder. I can run it at 1000 RPM, and that's slow enough for this small 6mm diameter Edgefinder, so I can locate my position to get my XY0. An alternative is, of course, a dial test indicator. I use this primarily to center on bores, but also to find edges and center stock. These are more or less jig bore practices, using a dial test indicator to center on parts. Takes a little bit of practice, but it's not really slow, and it's very precise. But to be honest, an Edgefinder is darn good. And again, this is just a CNC router. I'm not doing any jig bore precision work on this machine. I can run it at 1000 RPM, and then I can edge find as usual, using the pendant. Now we can take this out. To hold the Edgefinder, I'm not tightening down the collet nut like crazy. It usually is good enough to tighten it down just by hand, holding it like this and tightening it down, just so it's snug in the spindle. Now we do our collet change. One thing about ER collets, not only the taper needs to be clean, but also the collet nut, because it has a taper on its own in here. This taper down here, this is what locates the front of the collet. That's important to keep clean too. Same goes for the collet. Blow them off, drop them in the ultrasonic cleaner, just keep them clean. And by the way, if you look down in there, in the collet nut, you notice that there is a ring, and this ring is eccentric. This is on purpose. Don't machine the ring, the eccentric ring, out of this nut. This is here to allow the collet to snap in and be removed. 1.5mm end mill, necked down for 8mm depth of cut. And we're good to go. Okay, let's have the machine measure the length of the tool. That's the touch probe. It doesn't have a tactile switch on the inside. It has a inductive sensor here, which is set up in a normal closed configuration. Means when you press down on it, it opens. It opens the circuit, and the control knows the length of the tool. Normally open is normally closed, so it's an opening switch. It's important to make it fail-proof against cable breakage. If the cable was broken now, and I tried to measure the length of the tool, it would right away say there is something wrong because the Z-axis didn't even move. Same principle as with emergency stop. Those are always opening switches, normally closed, because when you have a broken cable, the machine e-stops right away without hitting the e-stop. If you have a normally open, means a closing switch as an e-stop, you have a broken cable, the machine doesn't notice, and then you hit the e-stop and the cable is still broken, nothing happens. So that's the reason why you're using normally closed for such applications. A quick look at my frequently used tool board. I had something like this always at work when I used to run CNC machines. When I ran the Datron CNC, I had a very similar board with the most used tool holding equipment, some tooling like end mills, and some miscellaneous stuff. So let's take a look at it. What I usually like to have at hand on a machine. I like to have my most used collets in the case of this machine, because it's a collet spindle. These are Farion precision type ER25 collets. 3, 4, 6, 8, 10, 12, and 16 millimeters. I also have a ER11 collet chuck with a straight shank. This goes in a 12 millimeter collet. And I use this for very small tooling because I have collets from 0.5 up to 7 millimeters here in 0.5 millimeter increments. I use this for small tooling and uneven diameter like drills. I have a set of taps and the tap drill here, M3 to M6, 2.5, 3, 4, 2, and 5 millimeter drill, a small tap holder. These holes are for countersinks. Currently there's only one here. Taper wiper, spindle wiper for the ER25 spindle. 3 millimeter shanked end mills, 4 millimeter shank, 5 millimeter shank, which are a little bit rare. A lot of 6 millimeter shank holes, 8 millimeter, and 10. Also, I have my Edgefinder here, 6 millimeter Edgefinder, and my Noga miniature indicator holder with a 6 millimeter shank that can go in a collet. I'm not a big fan of using these. I'm going to make me one of my indicator holders that I also have on the manual mill. This thing has too many degrees of freedom, way too many. This is ridiculous to be used on a mill. And a saw blade. This is to part off finished parts. Works quite well. Need to make a better shank. This one had a little bit of enemy contact. And currently there is a triangular stone sitting here. So that's all the tooling that I constantly need, apart from the wrenches for the spindle, of course. Very new end mills keep their protective cover on top. And once they're used or well used, they just go in this board. End mills that stick in this board are usually considered used, at least lightly used. New end mills always stay in their manufacturer packaging, like this one. I just got in an order of Göring end mills, and these stay in their packaging until I use them. And once I had used them, they go in a board like this, either in this one or down in the basement shop on the manual machine. The taps, of course, the machine cannot tap, but on a regular basis I need holes for fixturing in a base plate, in a fixture plate. And sometimes it's just the quickest to use a cordless drill the hole and tap it with the cordless drill instead of milling or drilling a hole and then thread milling it. So that's sometimes a very fast way of working. That's the clear benefit of having a ground level shop. At least some kind of decent view over the surrounding area. Not like just a bunker window from the basement. This is the window that's oriented towards the village. So that's quite nice. One question that comes up frequently is, can this router cut steel? And the answer is, as usual, it depends. Generally, I would say no. It's not made to cut steel, but you can make it cut steel. Here, for example, I'm helical interpolating 2 holes in 316 stainless steel, which works perfectly fine. Also, I did some contour work on the same part with a 4mm bullnose end mill and some undercutting and contour boring with a 4mm lollipop cutter. Do an undercut, 3D undercut in the bore. And that worked perfectly fine. But I would say 4mm is the upper limit of an end mill that's really usable on this machine in steel. Okay, that's one part with first side finished. Let's pull this off the fixture, and I will show you how these are made. First side fixturing is basically only these 4 screws. So here's the first part with the center section here tapped out. I will cut these tabs with a rotary tool with a small cutoff wheel. So all this material here in the center is not lost, not transferred into chips, and still usable. And also it reduces cycle time, of course, and it makes fixturing very easy. I ordered aluminium cut to size pieces, which are about 1mm in each direction larger than the finished product. Thickness is already done. This is precision aluminium plate. And on the manual mill, I drilled these 4 holes in a pattern, and I have a small fixture plate here bolted to the table of the mill, which I drilled and tapped with the same pattern. And these through holes are close enough dimensioned in diameter, so I don't need any further alignment. Put the 4 screws in, tighten them down. Workpiece 0 is center of stock. Center of stock and top side of stock. This is very feasible in this case because the precision plate here, the aluminum plate, is very consistent thickness. The first tool is a 6mm 3-flute carbide end mill, which will do the majority of the roughing and material removal, and also finish the OD. This is a Göring RF100 aluminium roughing finishing HPC tool. These run quite well and are not stupid expensive. Tool comes down to the probe and gets checked for length, and now we approach the work. First we contour the outside of the part with about 1mm depth of cut, multiple step downs. Followed by a finishing pass at full depth and 0.1mm step over. Roughing out the large pockets around the center piece, relatively shallow depth of cut but high feed. And now we cut the deep pocket to make room for the electronics. This is an adaptive tool path which keeps the side engagement always the same and is very effective on light duty machines like this. It does a helical interpolation down to depth, and then it's just shaving away the material with about, I think, 0.25 millimeters side engagement. This produces a very good chip that gets blown away by the MQL system and is not too hard on the machine. Now we change to a 1.5 millimeter 3-flute carbide end mill. I'm doing all the finishing with a 2 millimeter 3-flute carbide end mill because I need the small corner radius. I could also program it just to pick out the corners, but in this case I prefer to do the whole finishing with the small end mill. This takes its sweet time, but as I said before, it's a CNC machine. It runs unattended, so not a big deal. When I say that, that means that I can do, while the machine is running, I can make other parts on my manual machines. It's also finishing the floor surface here. And you can see the trailing spot of the MQL where the alcohol is flashing off behind the end mill. Same end mill also drills or helical bores the holes that get later tapped or stay just straight bores. The last drill we're running is a 4 millimeter 2-flute carbide end mill with a 0.3 millimeter corner radius. I need the corner radius to machine the large chamfer around the part here. I could also use a large chamfer mill, but that would mean one more tool change. And that way I can get away with 3 tool changes and have the machine run on its own most of the time. Apart from the manual tool changes, of course, but that's fine. 4 millimeter bullnose end mill, 0.3 millimeter corner radius, and I'm stepping down 0.07 millimeters each pass to create this chamfer. This gives a quite nice finish, and this is pretty much the only real thing that's later visible, so I'm taking my sweet time to get this chamfer right. Okay, we're back in the basement shop, and as you can see, the parts came out pretty nice from op first, or op 1. So let's do some detabbing, cut the tabs here. And what I found to work excellent, I've seen people use Knipex wire cutters or something like that to cut the tabs, but you're always in danger of damaging the part next to the tab, so we don't do that. What I found best is a rotary tool with a cutoff disc. Aluminium and the cutoff discs, of course, is a little bit tricky, but a piece of candle wax, so that works beautifully. It's relatively fast, very, very controllable, so no danger of damaging the actual part. Next will be to make a fixture to hold these parts for the back side. This is the fixture I came up with to hold the parts for the second side. It's just an old aluminum plate that was used as a super glue fixture, and I cut on the manual mill the internal dimension of the part as a recess all the way around. Also, I relieved this area here. You can see there is a little bit of a step, like 0.5 millimeters, that is relieved, so I don't have this huge contact area. And when we take apart like this, it slips right over here. It's located by the square boss that we left. Then we have 3 M3 screws that hold, then we have 4 M3 screws that hold the part to the fixture and allow me to do my fixturing. And I can take my offset, my work offset from either the fixture or the first part that I put on. It depends how I do the cam. I found when I make location fixtures like this for rather imprecise work, it's good to add a little bit of wiggle error. Otherwise you're fighting the parts on the fixture all the time. And that's about as little fun as it gets. I gave the XY of this locating boss here, the square locating boss. This is about 50 microns smaller than the actual measurement on the part. So it goes on nicely. Trust me, if you have a fixture that you're fighting, you're going crazy. In the same setup, I'm going to clean up the tabs using an end mill. So no need for manual rework here. I can just run a small end mill along here and clean all the tabs off. And these two holes here, these are 100 millimeters apart. These fit the 50 millimeter grid pattern on my CNC router table. Second side machining. I'm doing the second side completely with one end mill because I don't want to do the tool change. This is a 2mm 3-flute carbide end mill. I'm adaptive clearing away this large step on the outside. This is not the most effective way to do this. With a 6mm end mill, this would take probably half the time, but that would mean that I have to babysit the machine all the time. So that's why I run the smaller tool in exchange for a tool change, and I can do everything with the same tool. Here I'm cutting a groove for an O-ring. I'm just helical stepping down with the 2mm end mill to create this slot. And the last step is to clean up the area where we cut the tabs with the cutoff wheel. That's my setup to power tap the holes in the frames with a M3 tap. I have my two vices and I propped up some 1-2-3 blocks and a stripper plate that stops part from getting pulled up if I get a little bit careless. And this setup allows me to do all 4 holes just by turning and flipping the part around. As you can see, that goes quite fast. And the tap matting is a very safe way to do this. Takes maybe 40 seconds to a minute per part. That's a bucket of chips. Unfortunately, these, especially the adaptive clearing chips, are very, very light and take a lot of space. So this whole bucket of chips is like 2 kilograms, and the scrap value of aluminium is not so much. Yeah, but I'm still going to move it to the recycler and not just dump it. The finished frames, after some Scotch-Brite work, deburring, a very light edge break with the Scotch-Brite, and ready for anodize. 25 frames, first batch. We will make another 25. We decided to split the order up in 2. Otherwise, it gets a little bit convoluted. I have other work to do too. I need the CNC router for more than one project. And here is the frame after anodize with the 7-inch Raspberry Pi panel, touch panel, installed with the UI programmed. And here's the back side. You can see that through the threaded holes there are 4 screws sticking out. Those are used to mount the whole assembly in the peristaltic pump machine. And the 4 other holes where you can see the screw head, that's holding the Raspberry Pi display in place. I hope you enjoyed this mix of this rather weird mix of topics on CNC router. Thanks for the ongoing support. Thank you all for watching, and I'll be back for sure.